Okay, let's try to use now, class, the formula 12.2.3, which is LD over dB is equal to, uh, okay, let me look into the formula. Where's the formula? Okay, so LD over dB is 3 over 40, okay? Fy over F prime C. Okay, so this is an English unit, class. I want you to take note, no? So this is an English version of the formula. 3 over 40 Fy over lambda square root of Fc prime. Okay, and then we have here a psi. The factors, the factor of safety are psi t, psi e, and psi s all over c plus ktr over dv. Okay, so this is the formula. Okay, so let's check our, I think Fy is given, Fc prime is not given, so let's insert an Fc prime here. Let's make use of a 20 a megapascal, but this is English, no? So we will try to convert this later. Psi t is top bar. Okay, we have computed this a while ago. This is the top bar. Psi e is epoxy, so this is not given. Let's assume this is not, no epoxy coating. Okay, and psi s is for the size. What's the size of our reinforcement? It's 20, the main bar, no? So we're referring to the main bar diameter, which is dB equals 20, tama? Again, this is in millimeter, SI. Okay, so these are the given, the additional parameters we need in order to find out what LD is all about. Okay, our lambda is the aggregate type, so we have a normal aggregate, assuming that lambda is a normal aggregate concrete. So lambda is equal to 1.0. For top bars, what is your psi t? Psi t is 1.5. No epoxy, this is 1.0. For this reinforcement size, main bar diameter of 20. So let's look into the code. Okay, so I cannot memorize it, of course. So what's the reinforcement factor? Okay, take a look. For number 6 and smaller, it's 0.80. Okay, what is number 6 again? Number 6 is 20. So our psi s is 0.8. Okay, because this is 20 mm. Okay. Okay, did you get how to use the table here? Number 6 and smaller, so you just look here, 20 mm, and then you get 0.80 there. Okay, lambda is normal, so 1.0, automatic. In case the FCT is given, you have to compute for it. Okay? Okay, CB, kinumpute na natin kanina yan, no? Anong nakuha natin? So, let's take a look at what is CB. Okay, where is your CB? Okay, that's smallest. CB is 55. Okay, there's the value we computed a while ago. KTR is 3.271. Okay, let's check the limit for KTR class. There's a limit for CB plus KTR over DB, so we have to verify the limitations. So what's the limit? Okay, the limit for CB plus KTR over DB is 2.5. So we have to check on this. Okay, so we need to compute for this directly. Okay, so this is CB. So we have to compute it directly. 55 plus KTR is 3.271 over dB is 20. Okay, so this is CB, millimeter. KTR is dimensionless. There's no unit here, so you don't have to worry about it. Okay, so let's look into the resulting value. 55 plus 3.271 divided by 2. So this is 2.91. This is greater than 2.5. Therefore, anong gagamitin natin? Okay, we have to use this one. Okay? Because it should not exceed 2.5. Okay? Now, how do you convert English formula to metric formula or SI? So you simply multiply it by 12. Okay? So remember that. So we multiply the whole equation, okay, by 12. Okay? So as to convert your equation from English to SI. So this is now the SI or the metric equivalent. Okay, so 12 times 3 divided by 40 is how much? I think this is 9 over 10. Okay, 12 is 4 times 3, cancel 4, that's 3 times 3, 9 over 10. Okay, Fy is, what's Fy? 250, so we can substitute it, divided by 1.0 times square root of 20 megapascal multiplied by psi T is 1.5, psi epoxy is 1.0, and then psi S is 0.80 divided by CBKTR is 2.5. Okay, so what's your LD over DB? So let's compute for it. So this is 26.83 times, or wala pa. So LD now is equal to 26.83 times dB. Okay. So since we are in a metric, so you substitute 20 mm for your bar diameter. It's the bar diameter. So we simply multiply 26.83 times 20. You get 536.6 millimeter. Okay, so this answers your question on what is the length of development. Okay, so this length of development is the required length of development. So we have to compare this required with the actual. Okay, compare it to the actual value. Just like what I showed you on the previous video, we have here a drawing on how to okay, like this one, on how to get the actual values. Okay, so these are the actual values of LD here, starting from there up to this point here. Okay, LD, that's also the LD actual, and this is the one that we add the extensions, the factor of safety D or 12 dB, including the ln over 16 if it is at the point of inflection. So those are the comparisons. Okay, so in your laboratory next week, I'll give you your lab next week also, maybe on Tuesday. Uh, you will be computing the cutoff points by simply, I will show you how to do it using approximate computation at the point of inflections, because it's difficult to accurately compute for the point of inflection. I will give you a method that is easier on how to approximate it. And that point of inflection will show you how to compare the required LD with your actual LD. Okay? So this is now your actual LD. So always, your actual must be greater than your required. Okay? For safe design. Okay? The length must be greater than the required length of development, because it is much stronger if you increase the length of development. Let's say the required length of development is only half a meter, and you place there 1 meter, therefore there's no tendency for your reinforcement to be pulled out and to be causing splitting cracks. Okay, that's the reason why we have to check this. So instead of checking band stress, which are very difficult to understand in terms of values, we are comparing it in terms of length. And that is easier to see. Even the ordinary workers can see the requirement in terms of length than the band stress. If you tell your foreman that the band stress required is 100 psi, he will just look at you. He will not. He cannot measure 100 psi very easily. But if you tell your workers to place a length of development equivalent to 1 meter, then easily he can understand you. Okay, you see how the length of development term is used rather than the band stress. That's easier to apply. Okay, so ang kulang na lang dyan yung paano natin kukunin itong actual LD para ma-compare natin dito sa required LD. So I'll be giving you a couple of lectures on Tuesday to complete your your understanding, and then I'll give you your short or maybe your laboratory exercise. Then maybe on Thursday, you will be having your first quiz on the final term regarding deflection and length of development. Okay, so you start reviewing those two topics. Ayaw ko na mag-extend pa ng isang topic masyado mahaba para sa exam nyo. So you will be uh, having an exam on next week on this. Okay? So we still have one meeting to discuss all your concerns. So please, if you have questions, you write it down habang nagsosolve kayo ng problem or pinakikinggan nyo yung video. Kasi makakalimutan nyo yung question nyo pag hindi nyo siya sinulat. And we can discuss that on Tuesday for clarification. Okay? So our remaining lecture will not be so long. Siguro mga 15 minutes na lang yan para pakita ko lang sa inyo paano kukunin yung point of inflection. Yun lang ang medyo mahirap. And we will do it, we will try to do it the easier way. The easiest method I can show you, no? Not the book approach. The approach in the book is very mathematical. So I will show you an approach that is approximate but efficient, no? Which you can use both in design and in construction later after you graduate. Okay? So any more questions? I don't want to use all the time here in the lab because some of you here have no laboratory classes. I know that they are busy. So I'll cut my lecture at this point if there are no questions. Are there any questions?